So problem number 2, you're making flan for Professor Benson's birthday and want to add fruit to the top but are worried about crushing and ruining your dessert. The flan is a cylinder with a radius of r equals 0.13 meters and a height of h equals 0.1 meters and mass of 6.86 kilograms. So it looks like that. And the first question is calculate the density of flan. So density is mass over volume, which is mass over volume of the cylinder pi r squared h, and this equals to 1292 kilograms per meter cubed. Okay, the second question, when you slap the top of the flan, it oscillates up and down with a frequency of 2 Hz. Determine the microscopic stiffness of Ks of the flan. Hint, think of the flan as one big spring with a mass of 6.86 kilograms attached to the end. So which is the omega, which is 2 pi f equals k over m, which is, we can say omega squared equals k over m, and k equals omega times m. So k equals 2 pi f squared, frequency squared times mass, and this equals 2 pi squared frequency, which is 2 Hz, and 6.86 kilograms. This all sums up to 1083 kilograms per second squared, and this is the stiffness of the flan. So that's the next question. A fruit topping is placed in the flan which compressed by 0.01 meters. Calculate the mass of the fruit topping. Okay, so F net here equals Ks minus mg equals 0. Ks, because we're thinking of flan as a spring, Ks is the force of the spring and mg is the gravitational force, so it has to add, so it adds up to 0. So this means Ks equals to 0, no, mg, and m equals Ks over g. So m equal k, which is we found it from the last section of the problem, but the stretch is 0.01 meters and divide by 9.8 meters per second squared. So this goes to 1.11 newtons meter per square, so which means mass is 1.11 kilogram. The next question, calculate the Young's modulus for flan. Young's modulus is F over A divided by delta L over L0, which is F over A times delta L over L0, right? So this goes to, if we plug in numbers, 1.11 kilograms, 9.8 meters per second squared, because F here is the weight of the flan, and then 0.1 meters, which is the original strength, divided by 0.01 meters, divided by pi 0.13 meters per square. So this goes to 2048.86, and this is the Young's modulus for this flan. So the next question, Professor Schatz takes a slice that is 1/4 of the flan, so which is the area, new area is 1/4 of the original area, and then how much does this flan compress if he piles half of the fruit from the whole flan on top of a single piece? So the new force is 1/2 of the original force, right? So since we had this Young's modulus formula, we can rewrite it as F divided by 2 A4 L0, and this goes up to this new formula. So it becomes delta L, new delta L equals 2FLO over AY, which is 2 delta L if you simplify it. So new delta L prime equals 2 delta L, which is 2 times 0.01 meters, which is 0.02 meters overall. Okay, so this is the extra credit one. Before piling fruit onto his piece of flan, Professor Schatz slapped the top of his flan and watches it oscillate up and down. Calculate the frequency of this oscillation in hertz. Okay, so the new mass is the 1/4 of the original mass, right? And the area was also the 1/4 of the original area, which is, we know that new stiffness of the flan is 1/4 of the original. So we know that omega equals new stiffness over new mass, which is k over 4 m over 4 under square root, and we can deduct this to k over m, which is the omega. So new omega equals omega, which is 2 hertz. So it doesn't change.